if then the experiments will be wrong. So that is how it is. And how is transmittance and absorbance? Am I audible? Hello.
Yes, sir. Audible, sir. Sir, audible.
Okay. It says the network is weak and all that. Okay. So there will be logarithmic related, as you can see here. Okay. So let us go further. I'm going slow now. I have no right to go slow because Professor Swami is waiting. Then once I understand, it is very easy for me to design an instrument, isn't it? What I do is I take a white light, any source with all the wavelengths possible. I use a monochromator, that is isolating a particular wavelength. I pass the light in such a way that the same amount of light falls on a reference and the sample, so that, and I detect this, the outgoing light, right? And if sample is there, then maybe it will be at that wavelength, it will be absorbing some light, so that I will be getting probably less number of photons here. By comparing them, I find out the intensities. These are some things that you would have seen if you are at the BSc level. You would have seen different kind of transitions, for example, in an organic molecule that can happen, and so on. Okay. I will not go into these details. Remember, only when a molecule which is there in the lower energy state, stable at a particular temperature, and absorbs light, it goes to the higher energy state. Okay, so that is important to note. So here a photon with large frequency, high frequency will be required. That is shorter wavelength. Whereas for these transitions, it will be fairly long wavelength. Photons will be required. Okay. So, for example, if I take a double bonded system, I'll not go into these details. It is not at the +2 level, or let us say, BSc level. But when electrons can move along, this is a resonance. Understand this is delocalization condition. No? This electron, a pi electron here, can go around here. So, if electron can move over a longer space, longer length of the molecule, then the transition energy drops down. Why it drops down is not something beyond our scope of our discussion today, but I can get a corresponding spectrum. For example, benzene, as you can see, the wavelength shifts to longer wavelength because there are 6 pi electrons moving around, and so on. Okay, so solutions will have a solvent effect because of the molecules interacting with solvents and so on. All this I'm skipping. For example, look at it. Suppose I take a linear conjugated polyene. What you see here is this. If there are 3 double bonds, the transition is here. 4 double bonds, it has moved to longer wavelength, lower energy gap. 5 much longer, much lesser energy gap, and so on. This goes on. Okay. So there are various descriptive terms. We will not go into that. We are only focusing on concepts. Same thing happens with cyclic molecules. As you can see, the bigger is the conjugation, the wavelength at which it is absorbing is longer. That means the energy gap is becoming smaller and smaller. Maxwell-Range is something you can understand later on. I'm not spending time on this. Dr. Mahanti, till what time I can go? So the way it is designed already, I explained to you. I can use a lamp source. No, I have to have the light first. So, but for UV visual spectrometer, normally you cannot go from entire UV range to visible range with a single lamp. Nowadays, those lamps are possible.
Sir, go on. 4:45 we can carry on.
Okay.
If it
okay. I'll try to finish by 4:45. So, okay. So as you can see here, normally people use 2 different light sources. One is for the visible region, one is for UV region with an overlap so that there is no gap in between. And I use a monochromator, the same thing that you saw. Okay. That was the older design of the instrument. Nowadays, it is possible. Nowadays, instruments have become cheaper. They are much more efficient and so on. The same UV visual spectrometer with the same kind of performance level, which was costing around 6 to 10 lakhs earlier, you can get around 1.5 lakhs very easily, extremely easy to use. You get the whole spectrum directly here without any monochromator requirement. You need a dispersing grating here, but then no moving monochromator. I mean, you need a monochromator, you need a grating, but if nothing moves, the whole spectrum gets recorded. So you can do that. So a few things that you need to take care, just keep it in mind. We'll not discuss it today. So there are a lot of care to be taken when you're going for chemical analysis with optical absorption spectroscopy. You have to choose the wavelength right so that the species that you are going to measure, it should have very intense light absorption at that point. The spectrum of that should be having a very big peak there. With respect to concentration, you have to be careful that the concentration is not large enough that you start going beyond the Beer-Lambert's law of validity. It should be lesser. The matrix absorbance, the background absorbance has to be taken care. Otherwise, data will be wrong. And if there are multiple absorbing species, you may not get a clean analysis that way, because suppose I got a sample and a B sample. Suppose I take a tablet in which there are two drugs together, combined drugs. Drug A will have some spectrum, drug B will have some spectrum. Then how do I find out how much of A and how much of B without separating? It is possible. If I got pure A and pure B from the corresponding data, I can figure out, but one has to be very careful in estimating that with regard to the choice of wavelength where you are measuring it. So we'll take another just 5-7 minutes to look at the reverse part of it, other part of it. Whatever I was talking about now is from the ground state, the molecule going up to the excited state, because there are no excited molecule there. There was no light earlier. Okay, light came in, molecule got up. That is the process we studied. Now suppose I put light, some molecules go up. How do they come back? That is very, very complicated. And that is why the more complicated a system is, actually more information you can extract if you understand the complications. Why I'm saying is, suppose I take a light molecule, it's a dark molecule, I put a light, it goes up to the excited state. And in the excited state, it will not stay long. No, it doesn't, it's not stable there. So what will happen is it will interact with its neighborhood, with all the molecules around it, quickly go to a little more stabilized state, and then come back. Time scales are important here. It goes up very fast in a femtosecond time scale, extremely short. When it interacts with its neighborhood, which is called relaxation process in the excited state, it takes around picosecond to nanosecond time scale. And then there is an emission, which happens in a nanosecond time scale. This is what is fluorescence, right? So now, if I look at fluorescent molecule, if I have the fluorescence coming out of this molecule, I am also understanding these interactions, which is much more fine, much more informative compared to the original UV visible spectroscopy. And that is where its strength is. We'll just quickly rush through the slides. The timings are important, etc., etc. If I have understood this photon, which I'm plugging in, which I'm using to excite, I have understood this photon, which is coming out by comparing the properties of these photons. What am I comparing? I'm comparing the frequency, the light energy, or energy of the photon, I mean. With the blue photon is high energy, red photon is low energy. I'm comparing the energy, I'm comparing the intensity, how intense the light is, and I'm also comparing the property called polarization property. Not only that, these three properties, I'll not go into all those details. These three properties will have corresponding time dependence, because I told you the time scale becomes very important in this. I can control these measurements at different time scales so that I can get a steady state property, time independent property, and a corresponding time dependent property. And fluorescence by itself is extremely sensitive. with the cheapest fluorimeter available, you can go right up to sub-nanomolar concentration levels easily. And this is something I will not discuss at all. I told you that the molecule that got excited in the higher state, it interacts with its neighbor.
Hello? Sir, you are not audible.
What happened, Devasis?
Due to some internet problem, Professor Mishra is disconnected. He is trying to connect very shortly.
Okay, restart the system. Please call Professor Mishra and ask him to restart. और yes, हाँ इसको कहो
Hello? Am I audible now?
Yes, sir, you're audible.
Extremely sorry, I don't know what is happening. I will share again. So, oh. I think there is some problem. But can I go ahead with this?
Yes, sir, yes, sir.
This level
No,
of
no need
resolution?
of, yes, sir.
Yeah, this is the largest I can make it. So let me finish quickly now in another maximum 10 minutes. So somewhere in the 1970s or so, this fluorescence spectroscopy was getting understood by its correlation with molecular properties, and which sort of brought out the strength of fluorescence spectroscopy. By 1980s, it was possible to, let us say, for example, measure distances in nanometer, distance scales within, let us say, a biomolecule or so, which is otherwise extremely difficult to measure by using suitable fluorescent molecules. Possible to image species. For example, this is a sensing algal concentration, let us say. So a lot of sensing and biomedical applications were getting developed by fluorescence spectroscopy in significant way. The kind of color resolution that you see here is impossible using simple optical UV visible microscopy, optical microscopy. But you can do that with fluorescence microscopy with different stains, different colors. You cannot do that. In a regular optical microscopy, you cannot go for more than 2 colors, maximum up to 3 colors, and so on. Say, for example, in an assembly of bacteria, getting all the 7 bacterial phenotypes in one go is impossible by any other means other than fluorescence. Imaging of drug distribution in a small sample, like, where light can even penetrate through the entire body of a mouse, then you can sort of image where a dye or a drug is concentrating in the mouse, and so on. The efficiency of cars that you are seeing is impossible without fluorescence. In a sense, the optimization of the engine is done through fluorescence. See, post combustion, if the engine is fired, there is a lot of chemiluminescence. Light comes out, and you can see the the distribution of the reacting species in the entire chamber. But pre-firing, before firing, how do you know the fuel and sample mix? That is not possible easily. There fluorescence comes in with planar lasers. Fluorescence can be used in a satellite kind of a scale. Suppose you go for morning sun, where light comes parallel to the oceans, and you're putting a satellite on top of Earth at 200 kilometers up or somewhere and start looking at it, you will see fluorescence from where you can see a distribution of alga without actually measuring sample from place to place. A huge kind of a snapshot over hundreds of square kilometers that is possible with fluorescence spectroscopy. With confocal fluorescence, I will not again tell you what confocal is. All that I can tell you is that I can have a small pinhole, different light energy, light photons converge at different distances. As you know, maybe it is known to you that there is a lambda dependence of the focal point. Based on that, there can be additional resolution. For example, this image of a single neuron that you see with so much of fine details was not possible before confocal fluorescence. Multiphoton fluorescence has come in. I will not go into detail of it. All that I can say is that, again, two red photons can combine under the influence of a molecule to become a blue photon, and blue photon means a higher energy photon. Okay, I can use lower energy photon to get a higher energy emission by combining lower energy photon, make it higher energy, then get a fluorescence out. A lot of applications there. This I will skip altogether. Okay, so there is the decay that I was talking about. In nanosecond time scale, the light comes back to the ground state. Once it gets excited, I can use this decay information for again making imaging and other applications, and so on. It's a very brief summary of what fluorescence spectroscopy can do. A corresponding thing is actually not possible with optical absorption spectroscopy, although it has its own strength. Fluorescence spectroscopy makes it stronger. So it so happens that my area of research is photophysics and fluorescence spectroscopy. So I spent a little longer time with it. It so happens that at this juncture, fluorescence spectroscopy has crossed boundaries which were considered theoretically impossible. Now, intelligent scientists have managed way of circumventing them, and in the process getting Nobel Prizes, as you know. So, and so on. Now I rest. If there are any queries, comments, I'll be very happy to answer.
If anyone has any queries, can raise his or her hand. I can allow her to ask the question. We can take one or two questions.
Shall I keep the slide or shall I remove it?
Remove it, sir.
Okay. It's a more like an awareness kind of a talk.
Yeah,
be
sir.
familiar with
Nice.
what can happen. So that should be. Yeah.
Anyone has any queries? Kindly raise your hand. I can allow you to directly interact with Professor Mishra. Yeah, Priti Bisoi, I am allowing her to. You can ask your question now. Priti Bisoi, you can ask.
You can unmute yourself. Maybe some problem with unmuting.
Okay, you can write your question on the chat box. Maybe there is some problem. Okay, now Professor Sajda Samal is with us. I request sir to summarize the talk of Professor Mishra.
Devashish, thank you for asking me to summarize the lecture of Professor Mishra. In fact, there was a lot to learn from what he said to be elementary. I also learned many things within this 1 hour lecture. One thing that was very interesting to know is that the cost of UV instruments have gone down to as low as 1.5 lakh. So my suggestion, I would like to suggest you, Devashish, that you may move to the government that in each district there should be a nodal college who will have this low-cost instrument and start practical, giving practical training to the students. And I think that will help a lot, because as our classroom teaching is very good, but the problem with our system of education is that we are very weak in experiments, because we do not have access to basic instruments. And that is the reason
Actually,
why.
Yes, sir.
Yes.
The UV, the 1.5 lakh thing doesn't have the UV component in it. It's only visible. That's why it is cheap.
Okay.
Otherwise, with the UV source, it will sort of go up. But for teaching purposes, I think there are some startups in this country who have started making them, and it may be possible to negotiate with them to bring down the cost if
Right.
if
Right.
at least the visible, just
Yes,
pure visible
yes.
spectrum.
Yes. So basically what I wish to say is that money component is not very difficult right now with our government. If we can move the higher education department, incidentally, the buses is also in some position to negotiate with the government, that we should have nodal centers where we shall give practical training to the students, exactly how to deal with the machine and how to use it. That really has become a problem, because otherwise our students are very brilliant. They learn everything so fast in classroom teaching. But when it comes to real experiment, we face difficulty. I faced a lot of difficulty myself. Going out, handling NMR instruments, 500 megahertz NMR instruments, we have to do everything outside in your own hand. It was a really difficult thing for me. So otherwise, Professor Mishra, I loved a lot from your lecture. It is your sobriety, your lucidness, they're all combined. And always I say that a good teacher, it becomes good only when he makes the worst student understand the things very well. So for that to happen, the teacher has to really be very thorough. So I also request those who are teachers and listening to these lectures to learn one thing, that let us not teach something which we do not understand. First, we need to thoroughly understand and then teach. With that, I thank Devasis for giving me this chance, and I thank Professor Mishra. You have been very kind to Odisha. Your role as an academician is exemplary, but in addition, your softness, your soft corner for the state is very much noticed by all of us. So keep us in. I mean, we really feel fortunate to have good friends like you who think good of the state. So at any level, kindly help the state to come up to a certain desired level, which is lacking, severely
I
lacking.
feel fortunate if I can get an opportunity to have anytime
Okay.
for anything.
Okay, sir. Thank you very much. So over to you, Devasis. Thank you once again. Please go ahead with the next.
Thank you, sir. Sir, there are two questions in the chat box. One from Devasis. Why fluorescence is significant in this type of spectroscopy?
No. Fluorescence spectroscopy itself is a spectroscopy. A spectroscopy, we talk about, number of light photons getting absorbed or getting emitted. In fluorescence spectroscopy, we talk about number of light photons that are coming out. In UV visible spectroscopy, we talk about number of light photons that are getting absorbed. And as a function of what? As a function of energy, which is typically represented as wavelength. So just as we talk about the UV visible spectroscopy for light getting absorbed by molecules, we talk about fluorescence spectroscopy for light coming out of the molecules. Otherwise, the basic philosophy remains the same. In fact, the instruments also remain the same, almost similar, not exactly same, similar. So that is a form of a spectroscopy, optical spectroscopy. Yes.
Sir, another question from Deepak Kapse from Maharashtra is that is it a fluorescence molecule can be nanoparticle?
Question, please, again.
Is the fluorescence molecule can be nanoparticle?
In fact, it so happens that there are a lot of nano systems, whether they are nanoparticles or whatever. There are a lot of nanosystems which are monitored, which are fluorescent by themselves. Especially, for example, quite a few metal nanoparticles are known to be extremely strongly fluorescent. Nowadays, there is a craze for using carbon nanoparticles, and a very large number of carbon nanoparticles are fluorescent, and so on. So, yes.
Okay, thank you, sir. There's no more question. And we are very much thankful to you for giving so much of valuable time. And the student must have been inspired by the talk. Thank you, sir. So now,
It's a swine. I will not be able to actually continue. Is that okay?
Sir, namaskar.
Yes. Namaskar. I have some
Namaskar, sir.
other work.
Thank you, sir. I was enjoying your talk only, sir. It's good.
Oh,
It's a lot of learning.
oh.
I am just I can tell a supplementary added just to your talk only, nothing, because your talk is really good and I was enjoying. No problem, sir. Thank you.
I have to leave now. So, yeah.
Thank you, sir.
thank you.
Thank you. Thank you. Thank you, Professor Devashish. Thank you very much.
Thank you, sir. Thank you very much. So now we have the second talk. We have with us Professor Sarath Kumar Swami from BSSUT University. He is a big brother, like for me at least. Whenever I approach him, he never said no to me. And he is a very nice speaker, I know. So now I'm going to introduce Professor Swami before his talk. Professor Sarath Kumar Swami is currently working as a professor of chemistry at Veera Surendra Sai University of Technology, Bulla, Sambalpur. Before joining to the present position, he served as an associate professor of chemistry at North Odisha University, Baripada, till September 2011. He was working as postdoctoral fellow in Department of Polymer Engineering, University of Akron, Ohio, US, after receiving his doctoral degree from Utkal University, Bhubaneswar. He was working as a visiting researcher at Indian Association for Cultivation of Sciences, Kolkata, and Jawaharlal Nehru Center for Advanced and Scientific Research, Bangalore, with awarding INSA Fellowship, JNCA SR Fellowship, and he has more than 20 years of experience in teaching and research in area of organic chemistry, material chemistry, polymer chemistry at UG and PG level. His area of research interest includes hybrid nanomaterials, reinforced polymer nanocomposites, nanocomposite hydrogels for drug delivery, etc. He has designed various nanostructured material for anti-corrosion performance, superconductor particle sensor behavior. So far, he has published 2 textbooks, 2 edited books, and contributed 34 chapters in different books of international report. He has also published 120 research papers in different national and international journal papers. He has credited of invention of 2 patents in US and India. There are 16 scholars who are successfully awarded PhD degree with active supervision of Professor Swami, along with 14 MPhil, 4 MTech, and 33 MSc students who have completed their thesis in different emerging areas of chemical science and nanotechnology. He has handled several research grants from Department of Science, Technology, and Department of Biotechnology, CSIR, Department of Atomic Energy, Government of India. Professor Swami has received several awards such as Boy Scout Fellowship, DAY Young Scientist Award from Government of India, and Samanta Chandrasekhar Award from Odisha Vigyan Academy, Department of Science and Technology, Government of Odisha, for his outstanding contribution in sciences. So we are now looking forward to listen to Professor Swami. So now, thank you, sir, for giving your time. Over to Professor Swami.
Good afternoon to all. Am I audible, Devashish?
Yes, sir, you are audible.
Okay,
Kindly.
thank you. Esteemed principal of the college, Denkar Autonomous College, head of the department, Professor Mahanti, my younger brother, my esteemed teacher, Professor Sasdar Samal, Professor Mishra, the first speaker and the eminent personalities of the state. And I think Professor Mahapatra, my colleague, in the line also, and other dignitaries and delegates, or I can tell attendees, my students, and all of you. I think I'll continue. The assist, still I am allowed for 1 hour, or you have reduced it?
No, you are allowed for 1 hour.
It's
You go
okay.
on.
It's
It's
okay. Yeah, I'll stick to time. Don't worry. I'll stick to time. Okay, fine. Then actually, I have been requested that these talks should be basically for the teaching level of the undergraduate and postgraduate students. And definitely, the IR is a basic tool. I can tell what I'm going to talk regarding the IR. It is a basic tool for all researcher, definitely. But to know the fundamental, it is very important. Otherwise, you cannot predict, you cannot identify of your own material, own compounds. Okay, let me share the slides without delaying. Okay, let me share the screen. Okay, I think slide is visible, right?
Yes, it is.
Okay, thank you.
You can make it
Full screen.
presentation mode.
Full
Yeah.
screen. I understood.
Yeah, it is
Full
now.
screen. Now it's fine. Okay, just I changed slightly to make it interesting that Fourier transfer infrared spectroscopy, a molecular fingerprint. Why because like a person, when you're putting my for any identification, suppose if illiterate person, even the literate, sometimes without even with signature, you are putting your thumb impression. Because why? Because person to person, the thumb impression varies. My thumb impression is different from even my brother, my family members. That is why it is very unique feature to identify a person. That is why I can tell molecular fingerprint. If you take a molecule, how can you take its fingerprint? How can you take its signature? That's very interesting. And for the student's sake, I'm telling you should know that if you know the infrared spectroscopy, definitely you know the fingerprint of the molecule or molecule, how you can identify the molecule so comfortably after synthesis. Okay, I'm going to the basics and some idea regarding this. Then I'll try to make it more simplified to reach at the student level. I know the most of the participants are the student. I think as the most of the honor students in Dhengadh Autonomous College, as well as besides these also other students, research scholars are there, it will be helpful. Okay, I'm going to my next slide. Before going to the outline of my presentation, let me share a story for 1 minute. I will share a story, then I will go to the topic. Okay, you see the gentleman, Sir Frederick William Herschel. Sir Frederick William Herschel is a man of Germany and later become the citizen of the. What he was doing, he was writing a music. Okay, he's composing a music. He's not a musician, but he is composing a music. During composing the music, when you are writing on the table, and there is sunlight is coming from some of the source. Okay, like suppose we are sitting in outside, sometimes what happen, the sunlight is coming on some of the source. What happened, there is a paperweight on the table, and when sunlight came focused to the paperweight, what happened, suddenly he found little bit warm after that. What is that? All of you have seen the rainbow, right? Rainbow is to come at the visible region. Okay, suddenly found the warm, and then what is the light? Okay, then what he did, that surprised. Where is this heat came? Okay, this heat came, later he found the heat came just above the red, because you know from violet to red, the region of the rainbow, or you can tell visible spectrum. It is starting just above the red. He felt the heat. Then he put the thermometer and did the small experiment of different region of the color. He put different thermometers, and suddenly he found he put another thermometer just beyond the visible region near to red. He found, and the thermometer is giving the more heat as compared to the visible light. Then suddenly he surprised and got excited to write a paper, which paper is published in 18th in Royal Society of Chemistry. And suddenly he didn't design as infrared spectroscopy. He found that a visible light who can warm or who can heat or heat visible light. Okay. And from the literature I have gone through it, even it is 18, up to long time, it was not named even infrared. It is infra means it's infrared because it's close to red region. That is why I made it infrared. Okay, I think this is a very interesting. Why? Because this is an invisible light which can heat. That means you can light, you cannot see it. Okay, and where is the application? You know that many of the CC camera, that closed circuit camera, if you'll see in many of the shops, even institutes and other areas, even the dark is to take the photograph. How it is possible? Because of the infrared region. Okay, that is a infrared. I'm not going to discuss regarding the detail regarding the infrared. I'm basically focus how infrared will help to identify a molecule. Because I made it a fingerprint of a molecule, how it is identified. Okay, now I can go to the outline of my talk. Definitely, I'll discuss the introduction and the theory that how the FTIR works really, and type of vibrations. Because you know when the FTIR when the infrared light is focused to a molecule, definitely the first is principle that the bond becomes vibration. Very interestingly, if you'll notice that suppose I can tell any one molecule, let us say benzene. Benzene contains carbon single bond, carbon double bond, and even the carbon hydrogen bond is there. Even the carbon bond vibration and the carbon hydrogen bond vibration is completely different. Suppose one molecule is giving 100 peaks or 100 kind of vibration, 100, suppose even 10 peaks or 10 vibrations, and each vibrations are completely different from each of the bonds. It's very interesting that same CH, same CC bond in alcohol gives different vibration frequency that if it is in aldehyde. In the CH bond in benzene, it gives different frequency that if CH bond present in acetone. Because each bond gives a definite or fixed frequency. That is from the starting I told, the infrared spectroscopy, it will discuss, definitely it will come to our mind, that is a molecular fingerprint. Okay, somehow I will discuss depending on the time. I will show the instrumentation and sample preparation, because in undergraduate level we know that how to prepare the sample, and of course the application in one slide. Then I will end up my talk. Okay, then spectroscopy is the study of, if you tell what is spectroscopy, it is study of interaction between radiation and matter. I am trying to make a simple note kind of things by which the student, if the PG or undergraduate students are in line, they can even produce in their examination. That point of view also I am trying to make my talk. Spectroscopy is the study of interaction between the radiation and the matter. When any radiation, electromagnetic radiation, the picture I have given, the electromagnetic radiation, this electromagnetic radiation that gives, when it is exposed to the matter, that is the interaction, and the result of the interaction is spectroscopy, is nothing. Okay, that is why spectroscopy is the techniques to use that determine the structure of a compound and study of the interaction between the particular electromagnetic radiation and the matter. And so many spectroscopic, known spectroscopy, they are UV, that just now Professor Mishra discussed regarding UV spectroscopy, NMR, IR, mass, so many. But I'll trying to focus in this next 50 minutes that IR spectroscopy, how it's measured the bond vibration in a molecule to determine the different functional groups. That suppose you are making a compound, how to identify what are the different functional groups, what are the possible interactions possible in FTIR spectroscopy. Okay, I'm not going to discuss more about the electromagnetic radiation. Electromagnetic radiation, starting from gamma ray to microwaves, I think it has completely discussed that in the lecture of the Professor Mishra. Just I want to identify this is the infrared region. If infrared region, if you take for the sake of the student, I am telling it is, we can divide into three parts. One is near infrared, mid infrared, and it is far infrared. Mostly this active region is mid wavelength infrared is required. If you take its 2.0 micrometer to 4 micrometers. And the appropriate frequency, the interesting part is that in this region, each molecule, each bond I can tell gives definite frequency, which is very distinguished and to identify the particular compound. Then it will tell, it's just I have given it is a symmetric, asymmetric, blend. I will discuss that what are the different kind of vibrations are there. Only thing that it is vibrating, creating energy. Energy creates the frequency. I will discuss that in detail. Okay. Then I already told that Sir Frederick William Herschel, he first identified the IR. I cannot tell discovered because discover is not a good word. I can tell it's identified because IR was there in the sunlight. Okay. What happened? If we see what happened and when IR observed. IR observed only that radiation interact with the molecular undergoing change due to the dipole moment. All of you know that what is the dipole moment, and it vibrates. As it vibrates or rotates. Okay, we can tell in three regions. If you see that the important region, if you convert this wavelength to corresponding frequency by simple formula H mu or Hc by lambda. If you put the lambda, you can get the mu frequency. The mid IR is 4000 to 400 centimeter inverse. It's a very known region. Known region. These are regions. If you tell near IR, mid IR, far away, far IR, then what happened in the near IR? The change in vibrational and rotational level. But electron transmissions are there. But if you take the mid IR, it changes the fundamental vibrational level and most of the molecules. That is why we are mostly the IR spectroscopy concentrated on this 400 to 4000 centimeter inverse. Okay. Now, if we think that what is the infrared spectroscopy, what is to do? Infrared spectroscopy, what is to do? And before going to detail of the principles, I can tell if you see that how it is done, that how it is it used to work. If the radiation of all wavelength, if material depends, if you expose through this material depend absorption of wavelength of different way. Okay, you will see that the simple, there is a that inside that, suppose you put some molecule, that is a vibrations. You see so many bonds, 1, 2, 3, 4, 5 different type of bonds, and these bonds that gives different vibration at a different frequency. Okay, then what happened? This cartoon that lets the light shines. It is shining to just can't see. Okay, my light is infrared. That means this is this is a light that you can see it. But this invisible light vibrates the bond. The important that each bond is to migrate in a definite frequency, corresponding frequency, and exactly suppose I told that one bond. Let this C double bond O. C double bond O present in aldehyde. C double bond O present in ketone. C double bond O present in acid. C double bond O present in acid derivatives. But if you start saying the C double bond O, this C double bond O, even it is the absorption frequency in aldehyde is different from ketone, different from acid, different from acid derivatives. Even very surprisingly, the different, if it is aldehyde, the formaldehyde, acetaldehyde, the C double bond O is different. That is why exactly I told that this is the each molecule give a definite fingerprint for particular vibration. Then very easily you can identify the molecules. Okay. Now what happened? What happened why these wonder things happen? That means what is the that interesting that how the different bond gives different frequency. Even the same bond, if we change the molecule, it gives different frequency. Okay, how it is happened and what is the principle? Okay, what is the principle of the IR spectra? Before going to the principle of the IR spectra, because just very simple principle, I'm showing you. I'm sharing the same slide. I think I have shared. I'm showing a video. Is it visible? My screen is visible. Devasis, could you please help me to respond?
Yes, sir. Yes.
Okay, I'm showing a small video. Okay, you see, what I've written is what is this infrared spectroscopy? The story of infrared spectroscopy being by Sir Isaac Newton. You can tell I was telling regarding 1800 that this another fellow has identified the infrared spectroscopy. Again, why I'm going to Sir Isaac Newton, the 1642, 1727. If you see, just I'm playing the video. Okay. I think it's better. Yes. See. What happened? That this is the light projection is coming, and suppose if you put a prism, then what is observed? That is a spectrum of visible lights. Okay, and some area close to the red, this region is infrared. I told if you put the thermometer, you can do heat. Okay, since the region is invisible, is human eye, we cannot see. We can see from the violet to red, but the area close to red is invisible to human eye. But already I told Herschel needed a way to detect it. Okay, then if there is a change in the, you see the difference in the temperature. Okay, suppose you put a sample. Okay, what happens if you put a sample? Remove the sample, heat becomes, this is the heating. Okay, suppose put the sample, you see the change in heating. This what you got, the delta T. Delta T is what? That is the interference that is due to the sample only. Okay, by changing the part of the spectrum that lines the sample, the Herschel showed that, you see, if we change the sample, even this delta T also be changed. Okay, if you see that how we'll do it, very simple way, I'm telling that let's just I am showing. Okay, you see that how this is exposed. This is visible light. I'm showing, already I have shown it. Okay, this visible light and this particular area close to the red region near infrared, if you see in the mid infrared region, then you can find like this. Okay, and this distance between two consecutive tops or crest, that you can tell lambda. If you change the lambda, if we change this line from near to mid region, you see, if we increase it, definitely the lambda changes. The lambda changes, you see the vibration changes. You see the vibration. If we change it, there is a change in the vibration. Okay, the interesting part. See, suppose in this region, it is, I already told, is 400 to 4000 centimeter inverse the wavelength. What happened? If we put the bond, I told that same bond also that gives different kind of vibration. I'm telling how we'll show it. What is the thing? This is a classical way. Infrared spectroscopy. I told dispersive infrared spectroscopy. Nowadays is not available. What is now available? I'll show you. What is the main dispersive? There is a source, and when you are putting a sample and reference sample, definitely the sample exposed to the sample and the reference sample, the light source detect that there is a flat mirror. You see the chapping mirror, and always there is a there is a rotating mirror, or you can tell moving mirror, another is fixed mirror. If the distance of the fixed mirror and the moving mirror is same, there is no interference. I can tell zero interference. Zero interference means you cannot see in the UV IR spectroscopy. Then what happened? Exactly what happened? You see, this moving mirror same as that of the fixed mirror. When there is no change in the dipole moment for the molecule like carbon tetrachloride, molecule like benzene. So that zero dipole moment, there is no change in the distance of that from starting from the that moving mirror to the fixed mirror. If there is a change, you see that if you, and the heat is coming for which it is gratting, and you are giving the change in the wavelength. But if we put the Michael interferer, I can tell that then you can get FT or Fourier transfer spectra. What happened to Fourier transfer spectra? What is the difference? You will see this Michelson interferometer. Then what happened? You see that is the change. Then it is directly the spectra is coming to particular compound. Then I am taking it to theory part. What happened? Why? What is the change? The basic change. See the model of a molecule. If we put the model of a molecule at the equilibrium length, okay, there is a harmonic potential. We know this this theory you have studied in physical chemistry, also in the physics. If we do frequency, that mu bar is 1/2 pi root over k by m. This is reduced mass. This is reduced mass and force constant. Force constant, that means this mu bar is directly proportional to the force constant and inversely proportional to the reduced mass. You see, if we change in the size, if a small size atoms, it vibrates more frequently. And when the size of atoms is big, definitely vibration becomes less. You see, this d is the distance. Distance, that means it depends upon the different factors. What are the factors? Size of the atom is one of the factor. Force constant is, that means the bond between two atoms is another factor. And the mass is also the another factor. Okay. If you think regarding the energy, if you see the, is very interesting that selection rule. If you observe it, half kx square, if you think the energy is half mu bar, then if you observe, it becomes E1 is 3/2. You see the change. Change is E0. And what is this? This is 1 h mu, one energy, you can tell, and this is another energy. This change interference that gives a peak. I will show you why the peak is towards bottom, towards top. Okay. The higher frequency due to larger force constant, if it is smaller mass, you see the distance, it becomes is different. That depending on the different vibration, it gives different. That is depending on the size. You see the size, it gives the potential and potential energy starting from here to expose suppose the atoms to another, and the energy, you see the different levels. In this molecular elastic model, particular, it's an elastic model that is I've done some software, that if you see the delta n, what is this? Transition delta n. Delta n, if you see, this is delta h and 2 h mu, that is overturn, and this is the fundamental. Okay. The main limitation, if we see the bond vibration, the limitation is due to that I told the dipole change. The example in hydrochloric acid doesn't have dipole change, it gives that. Okay. For particular things, I'm telling this is the summary that how it is. Then I'm taking you to direct to slide. You see this. Similarly, the mu is your 1/2 pi is k by mu. Okay. This is 1/2 pi k by mu. That means mu is your mass m1, m2, m1, m2. That I told CH bond, then C carbon mass into hydrogen mass divided by carbon mass plus hydrogen mass. That gives mu bar. So that gives mu or reduced mass. That what exactly we are observed. That means the change in frequency I told, if you change the bond, frequency changes. The change in frequency depends directly on the K inversely proportional to to root over mu, root over k, or root over mu, or directly I can tell mu depends on the k, mu inversely proportional to mu. The k is the force constant and mu is the wave number, that is the frequency that it gives. Mu is the reduced mass. Okay, that any molecule consists of atom or bond, we can tell this is analogous like a spring. If we'll understand better, if it is a, if we think bond, that bond as a spring and the atom as a ball. Okay, then this is the stretching, this is compressed. Better I can make it full skin. It will be easy to understand. Okay, then come to here. What is there is a selection rule. What is the selection rule in infrared spectroscopy? If infrared light is observed, that is a change in the dipole character. I have shown that how the change in the dipole character occurs. Okay, that is, if we put, suppose I am telling that dipole moment is 0. Let's carbon dioxide. It is symmetrical stretching, IR inactive. IR inactive means what? If you expose it, you will not get any bond. Similarly, in asymmetric stretching, that is also IR inactive. Anywhere, if we put that there is no change in the dipole moment, then you cannot get a feasible infrared spectroscopy for the molecule. Okay, how can you know that a vibration are infrared active or not? How can you know it? As a student, first you should ready to what kind of molecule you are going to expose to the infrared spectroscopy. If a molecule has a center of symmetry, then normally center of symmetry, like carbon dioxide, I told the example is the center of symmetry. Acetylene. Okay, when the vibration are centrosymmetric, they are inactive. Okay, and infrared, but it is Raman active. Raman is a different story. Raman spectroscopy, I am not going to discuss. Then just I told, because the Raman spectroscopy, that is also in this region, but just for the particular lecture, I will concentrate in the infrared spectroscopy. But I would like to say that when there is a centrosymmetric, they are inactive in infrared, but you can identify in the Raman spectroscopy. That I want to say. Okay, but vibration which are not centrosymmetric are active in infrared spectroscopy. Okay, that means now we should understood that what kind of molecule I should have to be identified in infrared spectroscopy. Okay, then you see what are different motions of and degree of freedom. Degree of freedom is a different term. These are terminologies of the infrared spectroscopy. In the terminologies, in a three-dimensional space, when atom is isolated in 3 degrees of freedoms, what I can tell, if it is different type of motion, if it translational motion, the linear 3, non-linear also 3. Okay, if you think the rotational, I'm telling that exactly the book equation. But if you vibrational, it is linear. If you take the degree of freedom 3n minus 5 and 3n. What is n? N is number of atoms. Okay, then if you think regarding this, then you can compare that what sort of molecule have. For example, I am taking an example of the, suppose methyl alcohol. Okay, see this slide. Suppose methyl alcohol. Methyl alcohol, see the previous slide. First you should decide whether my molecule is linear or my molecule is non-linear. If it is linear, equation 3n minus 5. If it is non-linear, then 3n minus 6. Suppose you put tilde, how many possible vibrations are possible in methyl alcohol? If it is methyl alcohol, it is CH3OH, 1 hydrogen and 1 carbon, 4 hydrogen and oxygen. Okay, then if you, from that, if the number of atom is n, then accordingly you can fit the rule to get the how many exactly what is the number of vibrations occurs. Okay, then what is the fundamental? Suppose in XY2 molecule, XY2 type molecule, it is possible that the types of vibration, if we think that what is the possible vibration, then you can tell one molecule that should give one peak. But why the one molecule is giving the multiple number of peaks? Multiple peaks for the frequency. Why the number of frequency are there? Because of multiple type of vibrations. How will get the multiple type of vibration? Then if I'll take, I told the example, suppose you have ethyl alcohol, C2H5OH, just calculate 2C, 6H and O. Then you can calculate the 3n minus 6, 3n minus 5 rule. Then exactly you can get huge number of the vibrations. Where is the vibration come? That is possibilities is one is stretching vibration, bending vibration. This is available in the book. I am not wasting the time because this is the complete theory. This is symmetric vibration, it is asymmetric vibration. And if it is bending vibration, two types is in plane vibration bending and out of plane vibration. And in plane, there is a possibility that scissoring and it is rocking. And if it is out of plane, that is wagging and twisting. You see very easily. I told this is suppose two models. I can tell CH2. This is carbon and two hydrogens. Then scissoring, it's like just like scissors. I'm telling those are in undergraduate BSc honors students. It is easy to understand. Twisting, if we'll stretch one and pushing one, and if we'll pull one, you are pushing another one. If you push one, it's pull another one. Rocking, that means it is to opposite direction we are putting the rocking. And wagging also same way, that in one is plane, one plane, and another is that another bonding out of planes. Okay, that is why in summary I can tell it's if it is stretching, that either it is symmetric or asymmetric. If it is bending, then either it is in plane bending or it's out of plane bending. In plane bending definitely scissoring and rocking, and out of plane bending is wagging and twisting. Okay, see, I told that nowadays what we are getting, that is Fourier transfer spectroscopy. Okay, just now I have shown a video that how it is different. Okay, slowly I am telling that how to disperse power spectroscopy. What principle that earlier is to that exactly that molecule is to be identified. If a source of light, I told, if it is sample, definitely reference. Why reference is required? Because you must, in what frequency it is vibrating, you should have a reference sample. Okay, I told this is old phenomenon. Nowadays, this is not coming. I told that the FTIR spectra is came, but the radiation source is dispersed by gratting into single wavelength. It is monochromatic, I can tell. But nowadays, what is spectroscopy coming is polychromatic. Okay, it is single scan. Now, even we can scan up to 50 times per minute in FTIR. Okay, I'm showing it. How this is FTIR what? In particular, what I have shown in the last slide, you see the beam, if we put it, there is a change. You see, this is a moving mirror, I told, this is some sample mirror. Okay, this is a moving mirror and this is fixed mirror. Moving mirror, and if the distance you see, this distance and this distance is different. If I told from beginning, if both the moving mirror and the fixed mirror distance is same, there is no interference. If there is no interference, there is no vibration. That must be change in the distance of the mirror. How the distance is moving mirror distance changes in due to the moving of the mirrors. Why? This is due to change in dipole moment. Okay. Then you see what is the superiority of the FTIR over the dispersive IR. I told what nowadays what the spectroscopy we are using, that is FTIR spectroscopy, but it is how it is different from that dispersive spectroscopy was earlier it was used. Okay, this is non-destructive techniques. Now present FTIR is non-destructive technique. Just to put the sample, you will get the spectroscopy. It is simple and you can precise your measurement. That means what particular area you want, exactly that area you can precise for the measurement. Okay. And no calibration. Earlier it was calibration is required for the sample. Once first you have to calibrate, later that you can, no calibration is required. Even increasing speed, I told that even the dispersive IR in one scan, one sample is one scan, is you are getting very noisy spectra. But nowadays, even 50 scan you can do in 1 minute. Okay, definitely it is greater optical dropout and high sensitivity. Present is high sensitivity. Anyway, this is the first. I will not spend much time on this because how to identify the molecule in the spectra I will show you. Okay, the importance of the FTIR that identifies unknown material, and mostly it is what kind of functional groups present, what kind of bonds present, that is important. I told from beginning, suppose if it is, I told the example of the even OH present in the secondary alcohol, OH present in the primary alcohol, OH present in the tertiary alcohol, the vibrations are different. Even all three belongs to alcohol only. That means one functional group even gives multiple, one functional groups of different frequency for a different region. That's I told as a person fingerprint. Suppose my fingerprint is different from fingerprint of the other. Definitely, if it is, I told even the, you can tell tertiary butyl alcohol, isopropyl alcohol, ethyl alcohol, they are 1 degree, 2 degree, 3 degree alcohols. But they are OH, CO, even OH vibration, CO vibration is completely different. I will show some example. And case study, if possible time, definitely 10-15 minutes, I'll give you some case study. Determines the ammonite component in the mixture. Okay. What is the typical of FTIR spectroscopy? If you will see, there is a change in the resulting spectrum. If you will molecular absorption, the transmission creating the molecular fingerprint. If you will think regarding this is the scanning, you can get the different vibrations for different bonds. Suppose OH, CH, CO. Don't think only 3 is there. Okay, this is the number of. I told the number of vibrations you can get for particular compound C. This is alcohol. This CH, hydrogen, carbon hydrogen bond, and there is a, you see there is a CO vibration is here. That if you will see that two kind of, I'll go to it, why these spectrums are towards the this way or in opposite in that to height way, that I'll show you. But this way, that how the FTIR spectra gives. But I told that you can have the absorption mode and transmittance spectrum mode. If you absorption, then if you will see there is a peak, you can see top towards off, and it is the peak towards the down. Okay, that depend upon setting you can do. An IR spectrum usually plotted using the transmittance, and absorption band appears at the dips. That means this side, this B type, this spectrum used to come in this way rather than the maxima. We can tell this is in the form of a dip. Okay, called it is bond, but you can take also the absorption spectrum. Okay. What is the FTIR active bonds? How can you know it? Okay, I can tell 3 type of bonds. Sometimes very weak, medium, and strong. Then you have a question that how you came to know that it's a weak bond, it is a medium bond, it's a strong bond. That depend upon the diff. You see the diff, small diff, and big diff, and medium diff, and big diff. That depending on the height, or I can tell crest of the bond, it is either weak, medium, or strong. Okay, what is the different? It is like suppose strong polar bond like carbonyl compound, medium polarity and asymmetric bond with medium bonds. Okay, that weak polar and symmetric bond produce a weak bond. For example, this is a strong bond. This is weak bond. Okay, that depends. Then it's a medium bond. CN is medium bond. Then there is a question. Then, sir, how came to know that if it is strong, it is medium, it's weak? How can you know? The strong, medium, weak, that depends on what? It depends upon the what? The polarity and the symmetric bond. Symmetry and polarity that gives the weak and medium or the strong peak of that. Okay, this is the example. I'll show you that how this has happened. Already I told that this slide I will skip this slide, but quickly I am showing if it is there is a harmonic oscillation, then there is a fundamental band, there is a fast overturn, and you can tell a second overturn. The theory already I have shown in the video part. Okay, see the sharpness of the bond when it is narrow, when it is broad. You can see the different kind. you see, sometimes you can see a peak like this, sometimes you can see a sharp peak like this. Okay, the narrow bands are thin and pointed, okay, like a dagger, you see, and broad bands are wide and smoother. How it is? The typical example that broad band is displayed by OH band, okay, is found alcohol and carboxylic acid, and it is sharp band, that is, you can tell narrow bands, that it is found in other kind of bonds. That means two type of bonds. Don't be confused. That is either a sharp bond or it is a narrow bonds. That depends upon, I told, that depends upon the interference. How much of interference you are putting and particular bond, the observance of the IR light and interaction that gives whether it is bond is sharp or it is broad. Okay. Then I think this slide already I told I'm taking it to some other slides. That is, suppose a transmission band. Okay, you see, that is a OH stretching. Is normally it is coming, it will put that 3200, 3400. You see the peak. It should be like this. Okay, how can I know? You see, if you think regarding that region, that NH stretching, then you can tell the peak is like this only. Okay, that depends upon that when I can observe the sharp peak, when I'm observe a broad peak. I completely depend upon how the UV spectroscopy is observed and how it gives what is the change in the interference. I told from the that from the beginning of my slide, I told there is a change in the interference. That nature of interference, polarity, that gives the nature of the bond. Okay, that is why if you will see a infrared spectroscopy, the different height and different deep of the bond is different. Sometimes it is very strong, medium, and weak. The strength and the nature of bond complete depend upon the difference in the interference. Okay. In overall region, if I show that how it works, then when it is medium, when it is either it is stretching, and this is the suppose example, you see, and suppose it is alkene aromatic, suppose it is aldehyde, that depends upon whether the stretching, if I am starting from the 4000 to 400, okay, where is the peak, which particular peak in which region. This slide looks complicated, but it is just for your remind that even you can take a snapshot of the slide, by which it is easily you can understand, you can remember that. But then you can tell, sir, why shall I remember it? Why it is in the higher region? Why it is in the lower region? That depends. I told that frequency, whether it is 4000 region or it is 400 region, that depends upon that factor. I told mu bar value directly proportional to the bond constant or bond strength, or inversely proportional to the reduced mass. That gives the idea. And again, the stretching is at the higher frequency than the respective bending. That is why depending on the nature of vibration and the type of bond and what kind of atom exactly involved in that bonding, I told carbon and hydrogen, carbon and carbon. The bond is different. Why? Because that is single bond. Carbon, carbon, single bond, carbon, hydrogen, single bond. Then in this case, if the bond is same, then we have to calculate its reduced mass. Reduced mass, I told the reduced mass formula already in the slide, that reduced mass, if it is more reduced mass, mu bar will be less. Then it will be in the 400 region. If it is higher reduced mass, it will be in 400 region. So lower reduced mass, definitely in 4000 region. Then suppose carbon-carbon single bond, carbon-carbon triple bond, double bond, and carbon-carbon single bond. You see, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. If we increasing the bond, the single bond, double bond, and triple bond, when you are increasing the bond strength, definitely it is higher frequency. That means more energy is required for the vibration. Definitely one bond needs less energy. If it is two bonds, it's more energy. Again, 3 bonds, it is more energy is required. If more energy, definitely more frequency. Okay, that depends upon the 4000 to 400, which frequency, that you can easily identify that what particularly that depends. Okay, that My concern that only depends that what kind of bond is it. If it's bond, just to think the bond as a spring and atom as a ball, then you can identify the mass of ball, strength of bond, maybe double bond, single bond, triple bond. That gives also that idea whether it will appear at the higher frequency, or higher frequency means I can tell 4000 region, or it is 400 region. Okay. This slide looks complicated but easy to understand. If we think regarding you see this carbon-carbon double bond, carbon-carbon single bond, carbon-carbon triple bond. If we think regarding, suppose there is, you see, there is a NOH here, OH, NH, that is also change. Why change? That depends upon the what? And even even the OH in the primary, secondary, tertiary, that is also be different. Okay, I'll show you that how it is. Okay, how it works. You see, suppose if you'll see the particular compound, then the different compound that I can show this video. I have some idea that another 5 minutes I'll show you that how the particular compound you can do. Okay, you see that this how it vibration. This is bent and symmetric stretching, asymmetric stretching. I'll show you a particular compound. Let it be there. Suppose exposed to particular compound. Okay, I'm sorry. Yes, suppose this is hexane. Okay, this is hexane. Then for definitely compound. Let's take example of the hexane. Okay, hexane. You see, this is the structure of the hexane. This gives regarding these peaks that in around I can tell 2900, 500. This is due to CA stretching. Okay, if you think regarding this, you are coming. That is 2872. It's CS2 stretching, and we can have this stretching. If you think regarding this, if we particularly if we change it, if we see this CH, it is coming 1460. It giving the CH3. There is that CH present in the I can tell CH vibration present in this CH2 and this CH3 also that different. Okay, that depends upon what? That depends on the same factor. That depends upon that bond strength and change in the interference. Okay, when you see that suppose another same things, if we think that in the fingerprint region, that is also different. Okay, that means that particular bond, suppose CH if I'll take, there is a possibility that CH vibration, and that depends upon the exactly that what we are showing, that same CH, that stretching, even it's stretching, symmetric stretching, asymmetric stretching, that gives different. And even it's bending, you can tell different 4 kind of bending, that gives 4 kind of vibrations. Okay, then I'll show you some of the compounds, how to determine the functional group. Very simple. That suppose then there is a question that suppose number of peaks I'm getting for particular compound. I'm showing the number of IR absorptions. Then which absorption is the most characteristic absorption for to identify? Okay, see, for example, let's take one simple example that alkane, the functional group IR spectrum, that it is a CC, CH, and CH bonds is there. Okay, if we take a simple, let the hexane I am showing in a fixed picture, that video I have shown, but fixed picture you see, this is coming around 2960 to 2850 CH. Okay, this is due to what? CH2. Okay, this is 2 type of CH bonds are there, CH3 and CH2. Okay, then you can find out. But there is a CC vibration is also there. That CC vibration that gives around 1300 to 800. Then you can tell, sir, how can you know that way? Which one is CC? What is CH? Why it is different frequency they are giving? Again, I am telling the same frequency, that mu bar, that depends upon the 2 factor. One is bond strength, or you can tell, and another is reduced mass. Depending on that, it is giving. Okay, It is giving. Similarly, if you are, you can get a whether this compound is straight chain or it is a branch chain. That if it is alkane having the branch chain like geminal dimethyls, that two methyl groups are attached. In that case, you can get a 1380 in the doublet. You can get. If it tertiary, three methyl groups are there. Okay, that is also different. I told, depending on the nature of the group, the vibration also be different. Okay, suppose it is alkene. Alkene main thing is to identify the double bond. Okay, if we simple, if we double, I'm saying the fundamental. There is no research. Directly you have to produce in the examination to identify it. Suppose two delene. I'm telling 1, 2, 3, yes, 4, 5. See, this carbon-carbon double bond is here. Is carbon-carbon double bond stretching is 1640 centimeter inverse. Okay, but the hydrogen attached to carbon-carbon double bond and this CH bond attached to carbon-carbon single bond stretching is different. You see, the hydrogen attached to carbon-carbon double bond it appears little bit more. Why? Because this carbon-carbon bond distance is less. Carbon-carbon double bond distance is less than that of the single bond. If this distance is less, then hydrogen is more close to the carbon, which needs more energy for the vibration and frequency a little bit more. But in the CH2, you see little bit less. That depends upon what? This bond length. Again, I told that bond length, if a bigger bond, definitely easy to vibration. If the small bond, it is difficult to vibration. I told completely to think, if you put in your mind that it's a bond, it's just freeing. Okay? If you think, then easily you can identify. If you see a spectra, if you from the machine, if you put the this particular compound, you can get the spectra. But how can you identify the particular compound? Then you can get these kind of spectra. Okay. Now, 1, 2 more example before concluding. I'll show you. I told that 2, 3 case study to show you the picture only. You can identify the spectra. And suppose you can take an alkyne. Alkyne, most important is carbon-carbon triple bond. You see, carbon-carbon triple bond is coming around 2119 centimeter inverse. 2119 centimeter inverse. Okay. But here if you see the CH bond close to carbon-carbon triple bond. That means triple bonded carbon hydrogen is coming very high, 3313. Okay. That depends upon why. Because if we remember in the double bond in the last slide, if you see the double bonded, the hydrogen attached to double bonded carbon is 3033, and the hydrogen attached to carbon-carbon triple bond, you see, is coming around 3313. Why this is change? Change is depend upon the carbon-hydrogen bond. The CH bond, the hydrogen bond distance or bond length, I can tell, it's from the triple bonded carbon and the double bonded carbon is different. That is why you can identify the particular compound, that what is the characteristics peak. I can tell if you one peak you have to identify, then that is one carbon-carbon triple bond. One peak, suppose you can tell one peak is carbon-carbon triple bond. Then you can tell how can you distinguish two, suppose if it is a, suppose I can tell it 1 octane, 4 octane, that means it is terminal carbon-carbon, that terminal triple bond is there or triple bond within the chain. If it is a terminal triple bond, you see there is a terminal triple bond, acidic hydrogen is present, I can tell. This acidic hydrogen, if it is present, then the CH bond and there is no hydrogen attached to carbon-carbon triple bond. Then if you are getting the peak at the 3313 centimeter inverse, then easily you can tell there is a hydrogen attached to the carbon, triple bonded carbon. Then definitely you can guess that the carbon-carbon triple bond at the terminal position. Okay, but if it is the middle of the that chain, then very fundamental. It's I can tell the chemistry idea, organic chemistry idea, even the +2 chemistry idea, that you can know that how can you identify what kind of bond present in my compound, that I can easily identify. Okay. See, if it is halide, that is also different. You see, if it is carbon chlorine, carbon chlorine, carbon bromine, carbon bromine, carbon iodine, you see carbon fluorine. If you see, carbon fluorine is coming 800 to 600. Carbon bromine is 600 to 500. Carbon iodine is 500. Carbon fluorine is higher than the chlorine. Why? What is the reason? Again, the reduced mass. Because the bonds, carbon chlorine bond, carbon bromine bond, these depend upon the mass. Okay. This mass, definitely iodine is more reduced mass, definitely mu bar will be less. Bromine's mass is little bit less than that of the iodine, then it is little bit higher. Chlorine mass is, again, it is less than that of the bromine, it is little bit higher. Fluorine is smaller mass and definitely it is higher at the intensity. That I told, the difference, so many factors are there. I told that mass is a factor, bond strength is a factor, bond length is a factor, strength of a bond is a factor. Again, this gives the frequency. And what affect the intensity? That depends on the interference. That the depth or the degree of the interference or magnitude of interference can change the intensity. But we are more concerned the IR can be identified by the vibrational frequency. Okay. See the alcohol and phenol, they're alcohol and phenol, if you take, no, it's different slides. I think the spectra is not belongs to alcohol and phenol. Okay, there is a, you see the difference between the alcohol and phenol. Alcohol and phenol, that is a free OH group and type of vibration is OH. And even we can identify if it is intermolecular or intramolecular. If you start, because I think that's 1 hour is very less to for the complete prediction of the infrared spectroscopy for identifying organic molecules. I told, suppose if you keep on dilution, that is interaction between the solvent and the solute. This interaction, if there is an interaction, then you can tell it is intermolecular hydrogen bonding. Sometimes suppose you have a intramolecular hydrogen bonding, suppose COH group is there, OH group is there. Then suppose salicylic acid, that is intramolecular hydrogen bonding. This intermolecular and intramolecular hydrogen bonding can also be distinguished. How? If you change on the dilution, there is a change in the mu bar value, it is intermolecular hydrogen bonding. That is why the IR not only, the FTIR not only gives to identify the functional group, that also gives the interaction of among the functional groups in the organic molecules. Okay, that is why if it is, again I told, if it is 1 degree, 2 degree, 3 degree, that also be distinguished. Very identification. You see the CO stretching is, if it is primary, secondary, tertiary, definitely you see the CO stretching is very strong peak you can get in 1050. If it is secondary, then it is 1100. If it is tertiary, then 1150. Again, it is, if it is phenol, it is 1200. That is an increment of 50. You see, 50 increment. 1000, 500, 1100, 1150, 1200. Okay, that's a good increment in the 50. Because why? Because this is what, why primary, secondary? Because that depend upon the CO. CO breaking, you remember in the CO breaking in tertiary is more energetic than the secondary than primary, because that you can remember the reactivity of the in the CO breaking, the tertiary is more than secondary, more than the primary. If OH breaking, then primary more than secondary, more than tertiary. This simple chemistry, simple organic chemistry idea will give the enough understanding of predicting the FTIR spectra. Okay, almost at the end of my talk. Similarly, ether, I'm not going to that. Ether also, that even the, you see the epoxy ether and the even the ether CO stretching is different. That is also gives different peak. Okay, the aldehyde ketone, similar way, that I from beginning I told aldehyde ketone both contain C double bond O, but that is different. Simple chemistry and that nature of functional groups present in the aldehyde ketone, that gives the idea that how they are changed. That you see the acetaldehyde and formaldehyde. One example, that formaldehyde gives 1750, where that of that acetaldehyde, that is 1745. It is a little bit, you see, the less frequency, it gives strong vibration. That depends upon what? That depends upon the this plus I effect. Okay, plus I effect. That is the environment of C double bond O also be different from the that what kind of group is attached to particular bond, that also affect the nature of vibration. Okay, then I'm going to directly take into application because already I'm approaching 1 hour. These slides, if required, I can share to Devashish sir. Okay, the application of the spectroscopy, I'm almost at the end of my talk because I'm approaching 1 hour. The identification of organic compound, definitely structural determination. Again, I'm telling, if we understand from the infrared spectroscopy, it is not sufficient for the illustration of the structure. You have to take the NMR and mass because the environment cannot be distinguished by the FTIR alone. Okay, then quantitative analysis of the functional groups, that also you can identify. The distinction between two types of hydrogen bonding, I told, whether it is intra hydrogen bonding, inter hydrogen bonding, that also we can identify in the FTIR spectroscopy. Even that qualitative analysis we can done. We can do it the FTIR spectroscopy. And study of chemical reaction. How did the chemical reaction? I told, if it is chemical reaction, whether the hydrogen bonding is there, if it is chemical reaction, then you can identify in the FTIR spectroscopy. Okay. If it is double bond, suppose you are doing a polymerization reaction, polyethylene to polyethylene, double bond become a single bond. Then there is a change in the vibrational. C double bond O, you can get in monomer. If you take in polymer, there is C double bond, C single bond, C single bond, C double bond, C in the monomer. Then that becomes C single bond C in the polymer. That is how you can identify whether the polymerization is done or not. That means rate reaction also you can know. Study of keto-enol tautomerism, because keto, C double bond C, C double bond O you can get. In enol you can get OH. The OH is not present in the keto. That is whether keto-enol tautomerism, that also you identify in the IR spectroscopy. So many study of the complex molecule, that also you can get it from IR spectroscopy. If it is geometrical, is cis, trans, they are also be different. Rotational, what that means, even the detection of the impurity in the compound, that you can identify. Impurity of the compound, you can get a clear peak, or you are getting the peak along with that other peaks. That also you can identify. Now in your mind, that what we cannot identify. FTIR can I distinguish all molecules except enantiomers. Okay, but enantiomer we cannot identify in the FTIR. What we cannot do in the FTIR? FTIR can identify all organic molecules except what? Except zero dipole moment. The molecule having centrosymmetric structure, zero dipole moment, cannot gives any information in FTIR. Okay, I think almost I reached the end of my talk, and I acknowledge Principal Dhenkanal College for giving the privilege to Department of Chemistry, and Dr. Devashish Mahanti. He is my younger brother. I can tell he's very dynamic fellow, and now is the secretary of our Odisha Chemical Society. He used to organize such kind of that webinar regularly. I congratulate to Dr. Mahanti for this and keep it up. And other those teachers in other colleges, other universities, they will learn to for the propagation of the student. And the topic you have chosen is very important for the student, for undergraduate and postgraduate student and research scholar, I can tell, and my research group and participants in this virtual talk. Thank you all of my research groups also. Thank you. Now over to Dr. Mahanti. I think just 1 hour, 3 minutes I covered.
Yeah, you have taken exactly right time, and it's a very nice presentation. I think the students have enjoyed most of it. We can take 1 or 2 questions. If any question, you can raise your hand, and I will allow you to directly interact with Professor Swai. Or you can also type in the chat box. I can also ask you, Professor. And I request Professor Swai to share the slide with us. We will also share.
Sure. I can share this slide because it is very helpful for the student, and I think it is a course for the honor student, right?
Yeah. Okay.
Even PG also, we have also the course. Understanding of IR is very important. If you understand, you can identify, you can utilize direct utilization of this spectroscopy in your research.
Probably no question. So with us, colleague of Professor Sai, Professor Mahapatra, Priyanjan Mahapatra. So I request Professor Priyanjan Mahapatra to summarize the talk of Professor Sai within 2 minutes. Then we'll conclude our session with total thanks. Professor Devraj Korda is your team for 2 hours.
Thank you, Dr. Mohanty, for giving me opportunity to share my views. I would like to thank Professor S.K. Swain for the nice presentation. The presentation was really very fundamental, and I am sure the students, particularly the honor students and the first year of master degree, that is first year of PG students, will be benefited from this presentation. He has exactly covered the fundamental principle, the instrumentation part, the different of the studies that we can do with the help of IR or infrared spectrophotometer. Although the time, as he has mentioned, 1 hour is not sufficient, because in order to study the application of IR, I think 1 week, every day 1 hour, if you will take, it will take 5 to 6 days to cover the entire portion. But he has, I think, covered the fundamental part, and I am sure the student will be benefited from this. One thing I can request all the students, that since today you have learned about the fundamental principle of UV as well as the IR, the instrumentation part, the basic things that you can know. So you should go through your textbook, and at the same time, if possible, you go to the different virtual labs you will available in the YouTube and other site. You can see the good Central Institute, they have now uploaded some virtual labs on infrared and UV fluorescence, and so that it will today, since you're it is fresh in your mind, it will be very helpful for you to carry out your or to pursue your postgraduate studies as well as to research career. Once again, I thank Professor Swain for his nice presentation, and also all the staff and head of the department, Dr. Devashish Mohanty of Dhenkanal Autonomous College, and the principal of Dhenkanal Autonomous College, for organizing such a nice webinar. Thank you.
Devashish. Okay, before concluding, there are 2 questions. Let me clarify, very fundamental question. And I think Rajesh Kumar has written that, what is the significance of this broadness and sharpness? It's a good question. That when I can know that my peak is sharp, when I can know that my peak is broad, I told that completely depends upon the interference. That depending on the interference, you can tell. Ordinarily, if you see the OH peak looks like broad. Hardly you can get a sharp peak, and you can get a very small peak. That is a very difficult to identify the OH peaks. Okay, that depends upon the particular vibration, and depend upon the interference. And I told again that factor also theory. I told that overturn, fast overturn, second overturn, that also gives the different sharp and broadness. There is a video I have shown that how if a ball is vibrating and it's a harmonic motion, that how long it's cover, that depends upon the broad, and that depends that sharpness of the peak. Okay, this is one question. And second, another is Manisha. She's asking that why not the enantiomers can be distinguished? Exactly, it's a good question. That if it enantiomer, whether it is let it be D form or L form, the dipole moment is same. There is no structural change, but except the enantiomers that I can tell, suppose structural isomerism, position isomerism, all sort of isomerism you can distinguish. But enantiomer, there is no change in the bond. It is what happened from the principle we learn. From the principle only, that is due to change in the bond vibration. Bond vibration, there is no change. I told that that main hero is your dipole moment, which is creating all sort of things. From the beginning, I told that is the enantiomer. Both the enantiomers, there is no difference in the dipole moment, and there is that's why there is no enantiomers cannot be identified properly in the IR spectroscopy. These 2 questions in the chat box I have seen and clarified.
Thank you, sir. Thank you very much. Now I request Professor Devraj Korda Professor of Botany and in charge of head of the department Zoology to give a formal vote of thanks.
Thank you. Esteemed Principal Professor Ranjit Kumar Pradhan, respected Head of the Department Dr. Devasis Mahanti, convener of this program, resource person of the day, guest faculty of the department, respected colleague, dear participants, and students of the department. A very good evening to you all. I'm really delighted to have my share in this academic event organized by the Department of Chemistry. At the outset, I take pleasure in thanking Dr. Devasis Mahanti, who is also administrative officer of the college, for organizing this event and making it a grand success. My special thanks are due to Professor Ashok Kumar Mishra, Professor Sharat Kumar Swai for their outstanding talk on principal application of UV visible spectroscopy, fluorescent spectroscopy, and infrared spectroscopy. It was really lucid, inspiring, and very much informative. I am sure the discourse put by the esteemed speakers have benefited and broadened the horizons of the participants and all the researchers as well as students. The talk has certainly made us richer, side by side, made us more hungry for more knowledge. Once again, I take delight in thanking esteemed speakers of their presence and for the insightful talk. I also extend my thanks to Professor Sashadhar Samal sir and Dr. Priyaranjan Mahapatra sir for critical analysis of the topic. My thanks are also due to the guest faculty of the department, senior faculty member of the other departments, members of technical advisor team, and all the participants in the webinar for whom the entire program was exclusively meant. Last but not least, on behalf of the Department of Chemistry, I submit special thanks to our esteemed principal, Professor Kumar Pradhan sir, for his wholehearted support, guidance, and supervision. Thank you all, sir. Thank you. Jai Odisha, Jai Hind.
Thank you, Devara sir. Thank you all. So today's session has completed and we will again meet tomorrow 3:30 exactly. Thank you everyone.